I see. Okay, so what it is, it's terminated a recording. So now I have the first 5 minutes lecture. Then cut it off. It didn't tell me. So great. Uh, so or at least we'll have everything from now on. Oh, and then did you already? Okay, yeah. Okay, so other properties that we can advantage of. So the determinant of a product is the product of the determinants. That will be useful to us to get a practical way of computing determinants when we're solving systems of equations, because we'll have a situation where we're taking our matrix and multiplying it by some very simple matrix to perform a row operation, and that simple matrix we get a determinant of very easily. In fact, often it'll be 1. Okay. Also, the determinant of the transpose is the same as the determinant of the original matrix. So transposing does nothing. Also, the determinant of the inverse is 1 over the determinant of A, which means that, of course, it better not be 0. So in fact, if the determinant of a matrix doesn't even have an inverse. And what's particular to us for computing determinant is A is a triangular matrix. Upper triangular or lower triangular, doesn't matter. Then the determinant is very easy to compute. It's just the product of diagonal entries. Okay. Now, we'll talk more about eigenvalues later, but for those of you who are familiar with eigenvalues, the determinant is actually the product of all the eigenvalues. And that will be useful to us in our study of iterative methods. Okay. Well, in fact, if A is triangular, the diagonal entries are the eigenvalues. So these properties go together. Okay. Now, what's of particular interest to us is that, as I mentioned, a matrix only has an inverse if its determinant is non-zero. So this leads to several equivalent conditions when it comes to the ability of the matrix and its consequences for solving systems of equations. So I'll just state these equivalent conditions. So the following conditions I'll write down. If one of these is true, then all of them are true. So if a determinant of A is non-zero, then A inverse exists. We also say that A is non-singular or interval. So really these two are synonymous. So AX equals B, so it's a generic system of equations, has a unique solution for whatever right-hand side vector b you give it, and ax is equal to the 0 vector if and only if x itself is the 0 vector. So the only solution of this homogeneous system of equations is the trivial solution. Other conditions that are equivalent to these is for rank of A is equal to n. That is equivalent to saying that either the rows or the columns, so either one, are linearly independent. Because in fact, if the columns were not linearly independent, then you'd be able to combine them in a non-trivial way to get the 0 vector, so ax equals 0 would have a non-trivial solution. So the fact that you can't do that means that the rows and columns are actually linearly independent. Okay. Now, the fact that the determinant is the product of the eigenvalues is related to a nice geometric application of the determinant. For instance, the determinant of a 3x3 matrix can be interpreted as the volume of a parallelepiped, where the rows of a matrix or the columns define vectors that are the edges, adjacent edges of your parallelepiped. Determinant of an n by n matrix corresponds to volume of an n-dimensional shape. So it's like a generalization of, for instance, the volume of a box, you multiply length times width times height. So it's just a generalization of that. Okay. So any questions about determinants? All right. Now, in this next bit, I'm going to combine linear algebra with a little bit of calculus. If you have a matrix that depends on some parameter, so you can think of it as being like a matrix whose entries are functions, then you can take the derivatives of your matrix. Also, if you think of functions involving matrices applied to vectors, so you have functions of n variables, then you can take gradients and Hessians of those functions. So I'll give some particularly useful examples of that. Okay, so all right. So first, I'll deal with a case where the matrix A of t is n by n matrix where each entry aij is actually a function of t. So what you can do is take the derivative of this matrix, but that is just going to be, there's nothing special going on there. You're just taking the derivative of each entry component-wise. But things get more interesting when you talk about operations such as matrix products or matrix inverses. And these correspond to differentiation rules that you learned in calculus. So, for instance, the product rule so a derivative of a of t, b of t. Now, hopefully you remember your product rule from calculus, and that applies here, but here's where you need to be careful. So you have derivative a times b plus a times the derivative of b. Now, what you have to watch out for here is the order in which the matrices are figured, are listed. So since A goes before B in the original product, A or its derivative has to go before B or its derivative. So in a regular product rule, you're having one function times the derivative of the other plus the other function times the derivative of one, and it doesn't matter which order you write them, but here it does because matrix multiplication is not commutative. Now, there's also a rule for inverses. So, in the case where A is n by n and a non-singular matrix, okay, then what happens in this case is the derivative of the inverse is going to be minus the inverse times the derivative of A times the inverse again. Now, if you compare this to the rule for differentiating reciprocal of a function, so if I just have 1 over f of t, well, derivative of that's going to be minus f prime of t over f of t squared. Well, this rule is consistent with this because we have a of t inverse twice. So you can think of it as being like 1 over a of t, if I'm be very busy with my terminology. And then you have a derivative in the numerator, as it were. And then you have a minus. So again, it's just like with this rule, it's like a generalization of it. But again, you have to be careful about the order of multiplication. And the way you can get this rule is using a product rule, where you're using the fact that a of t times a of t inverse is the identity, and then you carry out the product rule and set that equal to the derivative of identity, which is 0, and then you solve for the derivative of the inverse. So this rule is a consequence of this one. In fact, it would be a fairly simple exercise and good practice to try to prove that. Is there any questions about these kind of differentiation rules? So now we'll take a different point of view. Because instead of dealing with functions involving matrices, or rather functions of a single variable, we deal with functions involving n variables. So now we get into multivariable calculus. So let's suppose I define a function p of x. So x is in Rn of that's defined to be x transpose ax. Now, in the case where n equals 1, that just specializes to d of x equal to ax squared. Now, of course, you know what the derivative of this is, right? A is a constant.
The derivative.
Of that, yes.
Yeah.
What?
Yeah.
Yeah, 2ax. Okay, so I'd be expecting something similar here. So what you would do is, this can be written as a sum. Okay, so A is n by n. So this is actually a double sum over all I and j of aij xi xj. And you can figure out the gradient of that by differentiating this with respect to each like xk, for instance. And these derivatives, each of these individual derivatives will be 1 or 0, depending on how the indices matched. And then you got to use a product rule. So I won't go through the whole process here because of time, but what ends up happening is the gradient of phi turns out to be A plus A transpose times x. And then if A is symmetric, which means that A equals A transpose, gradient of phi just reduces to 2A times x, matrix vector product. So you see how this is consistent with this. But you have to be careful about the lack of symmetry. If A is not symmetric, then you have to use the transpose. So you can see how it relates to the single variable case. And also, the Hessian of phi would turn out to be just, so taking the derivatives of this would be just 2a, because the Hessian, as you may recall from multivariable calculus, is the matrix of, actually, A plus A transpose, which is 2a in the symmetric case. The Hessian is a matrix of second partial derivatives of your function. And the Hessian is generally always a symmetric matrix. And sure enough, this matrix is also symmetric regardless of whether A is. Now, this is for quadratic forms. We also have the following. If I define psi of x to be equal to a dot product of x with a fixed vector b, well, then the gradient of psi is just going to be b. So just like we're taking a linear function, so f of x equals b times x, where b is a constant, derivative is just b. So it's the same thing here generalized to n variables. So this will be useful to us when we get to non-stationary iterative methods, because the gradient, you may recall from multivariable calculus, gives us direction of steepest increase, or minus the gradient is a direction of steepest descent. And that will help us design iterative methods that are guaranteed to converge. Okay. So questions about these differentiations? Okay. In fact, I think if you look in the yes.
Are these some things that we would compute using MATLAB?
Oh.
These things that we would have to compute by hand.
Oh. Well, the thing is, really, you'd just be making use of these differentiation rules in the design of iterative methods. So it's really more of an analytical device than anything else. So you wouldn't necessarily be computing, like, say, given a specific matrix, what is this gradient? But it's more of a theoretical tool.
Okay. Thank you.
Okay. rest of my notes. I'm just going to piece together the rest of my notes. Okay. All right. Let's see. Oh, here's a marker. Actually, let's just see if this marker is any good. Nope. Okay. What? Actually, this one's still good. I saw another marker. I thought maybe we could have two, but no. I have more markers in my office. Okay. So now, this is something that is not normally covered in a first linear algebra course. So now we're going to start getting into things that are new to you, and making use of some of the concepts that I've showed you to develop what is known as the Sherman-Morrison Woodbury formula. Really what I'm going to do is show you the derivation of the Sherman-Morrison formula, and then the Sherman-Morrison-Woodbury formula is a generalization of that. So I guess Woodbury came along and extended it. Now, so the problem is this. Suppose we have a matrix of this form. B is equal to A plus a rank 1 matrix. So this is called, you've seen this before, is an outer product. And since I'm adding it on to A, this is an outer product update. Also known as a rank 1 update, because as you will prove in the first homework, any matrix of this form, a vector times the transpose of another vector, only has a rank of 1. We're also going to assume that A inverse is known. So the problem we're going to solve that we use this Sherman-Morrison formula for is what is B inverse? So can we come up with a nice formula for B inverse in terms of A inverse? And in fact, this is quite useful for iterative methods for solving systems of nonlinear equations. I won't be able to get too much into that in this class, but I'll just write down the application in case you want to look it up yourselves. It's called Broyden's method for solving systems of nonlinear equations. I actually cover this in Math 561. Okay. But there are many uses for a Sherman-Morrison formula. Like for instance, suppose you're solving a system of equations, you've gone ahead and done that, and then the matrix changes just a little bit, like maybe one entry changes. How does that affect the system, the solution to your system? Like if you're solving Ax equals B, you've solved it, and then your B doesn't change, your right-hand side doesn't change, but your matrix does, just an entry here or there. What does that do to the solution X? Is there a simple way to update it instead of having to solve it all over again from scratch? We don't want to have to do that if we can avoid it.
So is this like sensitivity studies or something?
Actually, it could be used for that, in fact, to see how much B inverse changes. So really you could use it for practical purposes or for analytical purposes like that. Now, this is going to be kind of messy, but I think I have enough time to do it. Oh yeah, I got half an hour, so totally doable. And the reason why I like to show this derivation is we start with certain properties we want the matrix to have, and then we can use those properties to try to actually get a formula for the matrix. And it seems like something that shouldn't be possible, but it is. Okay, so first, if I define a vector x so that ax is equal to u, so x is equal to a inverse times u, then now I compute b times x. Well, b is equal to a plus uv transpose. So that's going to give me ax plus u v transpose x. Now, what's interesting about taking an outer product update and multiplying it by a vector is now v transpose x, what kind of operation is this? So if I just group these together. Yeah, it's an inner product or a dot product. So outer product times vector gives you inner product. So this is just a number. Now ax is equal to u, so I'll fill that in. And now what I can do is factor out the u. So this is 1 plus b transpose x times u. Nice. And this is b times x. So now what I can do is I'm going to multiply both sides by b inverse. So x is going to be, now this is just a scalar, so I can leave it where it is. I'm going to have b inverse u. But x is a inverse u. So now I have this. A inverse u is 1 plus b transpose x, b inverse u. Okay, so actually, what I really want is, I want to rearrange this. So I just move this constant to the other side. Okay, so this is helpful because b inverse is what I'm after. I have a inverse, so now I know that a inverse applied to this specific vector gives, b inverse applied to this specific vector, I know what I'm supposed to get. So I now know something about b inverse, because the idea is, in order to figure out b inverse, I have to know how it affects the entire vector space Rn. I've just figured out how it's supposed to affect a small one-dimensional slice of it. So that gives me something to go on. But now I've got to figure out how b inverse acts on the rest of Rn. Fortunately, there's a simple way to figure that out. Again, using this relationship between outer products and inner products. So suppose x satisfies this relationship, then v transpose a inverse x is equal to 0. Another way of putting it is x is actually perpendicular to a inverse transpose times v. So all I did was I transposed this and so basically what I'm doing is I'm taking the dot product of this vector transposed with x, and I'm getting 0. Now, when the dot product of two vectors is 0, it means the vectors are orthogonal, or perpendicular to one another. So if x satisfies this condition, fix my grammar here. Okay. And the thing is, this is some fixed vector in Rn. There's an n-1 dimensional space, subspace of Rn that is orthogonal to this vector. So in fact, in other words, most of Rn satisfies this. So, so from this, let's see what it gives me. So
Is that A inverse or?
it's A inverse here,
Right.
but I transpose all of this.
Okay.
That gives
So
me
it's
A inverse transpose. Yeah. Okay. So now if I compute B A inverse x, so that's going to be, so B is equal to A plus U V transpose A inverse x. So now I distribute this. Here the A and A inverse cancel and just get x. And then I get U V transpose A inverse x. But that's precisely what I said was 0. So this just equals x. So now if I multiply both sides by B inverse, I get B inverse x is equal to A inverse x. So I'll emphasize both of these conclusions here. So this first one tells me how B inverse x on a one-dimensional subspace of Rn. The second box tells me how B inverse x on an n-1 dimensional subspace of Rn. Between the two, I have the entire space Rn covered. I have enough information to figure out a formula for B inverse. Okay. Now, that doesn't mean it's going to be an easy task to get the formula. But now I can show you by actually making a problem a little more abstract how I can use these properties to get the inverse. But if I work on these directly, the notation is just going to get super ugly. So I'm going to use some extra symbols here to try to make it easier to see the construction.
Can you go back for a second?
Oh yes, sorry.
Thank you.
Yeah, definitely don't need to see me erasing. Okay.
Thank you.
Okay. Oh, it's still. All right. Okay. So, so a more abstract version of this problem is followed. Suppose I'm given a matrix C. We define D, another matrix, that satisfies these conditions. First, dW is equal to Z for certain fixed vectors, W and Z. And then we have dy is equal to cy for all y that are orthogonal to a certain given vector G. So in other words, G transpose y is 0. Now, before I solve this problem, I'm going to show you how this problem relates to the problem of finding B inverse. So I'm going to give a translation table, if you will. So C in here corresponds to A inverse. It's a matrix we know. D is B inverse, the matrix we're trying to get. W here corresponds to U in the previous discussion. Z is equal to 1 over 1 plus B transpose A inverse U times A inverse U. Okay. And G is equal to A inverse transpose times V. So this is why I'm not using the original notation, because if I use all these, it's going to get really ugly. So I'm just going to simplify the notation a little bit to see its even formula, and then we'll map everything back using this translation table. Okay. So now what I can do is just write down a formula for D.
Should the bottom, the denominator of D there be A inverse Y?
Here?
Yes.
No. Y is part of our new language. So, yeah, corresponding to what happened over here. Okay. Unless I. Oh.
Yeah.
Okay, here, this is not wrong, but it's misleading. This should be A inverse U. Well, which it is, but.
Okay, now I see.
Okay.
What did you just say was misleading? I'm sorry.
Oh,
What?
if you go back to the previous board, okay.
Sorry.
Here I have, hold on.
I'm not an idiot. It's hard to
There you go.
I know it's hard to pan. Yeah, V transpose X.
Uh-huh.
X is A inverse U. So in the notes, I had A inverse U down here, just to make it more
Okay.
self-contained.
Okay.
No. Yeah, I haven't switched any notation from the notes. Okay. All right. Any other questions before we get to the gist? Okay. So now here's a formula for D. So D turns out to be C plus Z minus CW G transpose all over G transpose W. Okay. Now, so why does this work? Because let's suppose that Y is orthogonal to G. So if I multiply both sides of this equation by a vector Y that's orthogonal to G, G transpose Y is 0. That would wipe out this entire term. And then I have dy equals cy, which is what is required. On the other hand, suppose I multiply both sides of this equation by this vector w. So I have dw equals cw here. And then here I have g transpose w, a dot product, which cancels with the g transpose w down below. So these are gone, and now I have cw plus z minus cw. The cw's cancel out, only the z is left. So again, I get dw equals z as required. So this satisfies both of these conditions, as you can verify for yourself if you're not sure from my verbal explanation. And sure enough, since you want the two matrices D and C to be equal on an n-1 dimensional subspace, it's no surprise that D is actually equal to C plus a rank 1 update, because this, in the numerator, is an outer product. It's a vector times a transpose of another vector. So we're just tweaking C a little bit to get D. So now I can use all this, use my translation table right here to write down what B inverse is. So B inverse, if I just map everything directly, it's going to be A inverse plus, okay, Z, which is 1 over 1 plus B transpose A inverse U, minus A inverse U hold on, I forgot this part. A inverse U minus A inverse U times G transpose, that's going to be V transpose A inverse, because I'm taking the transpose of this, all over G transpose, so that's V transpose A inverse, times W, which is U. So now I have a formula for B inverse in terms of A inverse. But this formula, it's a little bit messy. You can do some simplification, like for instance, using just simple algebraic manipulations, common denominators, things like that. And so I'll go to the other board and write the formula as is commonly known. No pen yet. Okay. All right. So what we have is what is commonly known as the Sherman Morrison formula. And it is B inverse, I'll just have the whole thing. So B is equal to A plus a rank 1 update, implies that B inverse is A inverse minus A inverse U, V transpose A inverse, all over 1 plus V transpose A inverse U. Okay, so if B is A plus a rank 1 update, then B inverse equals A inverse plus this rank 1 update. Okay. So how you might use this? So given the solution x if ax equals b, the solution y of by is equal to lowercase b. So in other words, we have the same system of equations on the right-hand side. We're just changing the matrix a little bit by rank 1 update. So we get y, which is big B inverse little b, is equal to x minus A inverse U V transpose x over 1 plus V transpose A inverse U. So you still need to know A inverse U. So U is some fixed vector value. So if you can solve that system, then once you have x, then y is quite easy to get. And then if you perform any other, if you need to solve this with any other right-hand side, again, once you can solve it for A, it's easy to solve it for B. Because then there's very little work involved here, hardly any operations compared to what you'd have to do to solve this system of equations, for instance. So in other words, making these tiny changes to A, these pinpoint changes, updating individual entries, there's no reason to have to start from scratch and solve the whole system again. Now, so that is the case where B is a rank 1 update of A. On the other hand, a rank K update is, so this is Sherman Morrison Woodbury formula. So B inverse, B is equal to A plus UV transpose, where U and V are matrices that have K columns. So UV transpose as rank K now. So then B inverse is A inverse minus A inverse U, identity plus V transpose A inverse U inverse V transpose A inverse. So that's a Sherman, Morrison, Woodbury formula. And you can see how this one closely resembles this one. The difference is U and V are matrices now. So this denominator here is no longer a number, it's now a K by K matrix. So instead of taking 1 over this number, we're taking the inverse of this matrix. And again, you have to be careful about the order in which you multiply things. But otherwise, you can see how it's a direct generalization of the Sherman-Morrison formula. So, so let's suppose you want to update K entries of a matrix. You can do it as, you can think of it as K rank 1 updates, or you can think of it as 1 rank K update, or maybe even fewer than K, and do it all at once using the Sherman-Morrison Woodbury formula. Okay. So any questions about all this that transpired here? So we see that orthogonality, when you have an inner product equaling 0, can be a nice tool for helping us to get things to work out in the right way and construct matrices such as this. The way this is used in systems of nonlinear equations, for instance, you're solving a single nonlinear equation, you can use Newton's method. And in that case, you're using a reciprocal of a derivative. For a system of nonlinear equations, you can again use Newton's method. And in that case, you're taking the inverse of a Jacobian matrix. But that Jacobian matrix is very expensive to compute if you do it every single iteration. So instead, you perform rank 1 updates of a Jacobian using the Sherman-Morrison formula, and that's what leads to what is known as Broyden's method. So that's a very efficient approximation of Newton's method that cuts down quite a bit on the expense because you're only computing a Jacobian matrix once instead of every single iteration. Okay. All right. I have 8 minutes. So what I've done at this point is I've finished chapter 1. Okay. I will get into the first little bit of chapter 2, so that'll put us slightly ahead of the game, which we might need later. Never know when a tornado's going to come through and cancel class or something like that. Okay. Okay. All right. So I'll start for a topic that's very important to us the whole semester. Vector norms. So for error analysis, it's going to be very important to be able to measure size of vectors and matrices. Now in calculus, you often use the Euclidean length of a vector, so square root of sum of squares, but there are many ways to measure the magnitude of a vector. Some are going to be more convenient than others in certain contexts. Okay. So I'll talk about vector norms today, and then we'll get into matrix norms on top of that on Wednesday. So a function that is suitable for measuring the magnitude of a vector is called a norm. So I'll define a norm using double vertical lines. Some books use just the absolute value. And this will be a function from Rn to real numbers. So this dot here, that's just a placeholder. So whatever vector we're taking the norm of, we put it between the double vertical bars. So not just any function can be a norm. So a norm, in order for a function to be a norm, it has to have these properties. So first, the norm of a vector cannot be negative, and in fact, it must always be positive unless the vector you're taking the norm of is the zero vector. So the norm of x is 0 if and only if the vector itself is 0. Second, if you scale a vector by a constant factor, then that scales the norm by the absolute value of that factor. So its responses you would expect to changes in length. And finally, we have the triangle inequality. The norm of a sum is less than or equal to the sum of the norms. Okay. Now, there are many functions that satisfy these conditions, but there's one family of norms that will be really the only ones that we're going to need. Let's see. Okay, so I'll define those, give a few examples, and then we'll stop. They're called the P norms. Okay, so the way the P norms are defined, so I use P as a subscript, and what we do is we take the absolute value of each entry, raise it to the P power, sum them all up, and then raise the result to be 1 over P power. So we can use this for whatever value P we choose. Now, here are some values of P of particular interest. So we have P equals 1, so the 1 norm, also known as the L1 norm. You could use whatever term you like. So that's just going to be the sum of the absolute values of all the entries. Then we have P equals 2. So the 2 norm, also known as the Euclidean norm. So it gives you the Euclidean length of a vector. So it's just the square root of the sum of squares. Okay. And then if we take the limit as P goes to infinity, so we get the infinity norm, what happens is the larger P is, the more of the largest component influences the value of the norm because of this exponentiation. So in the limit, only the largest element matters at all. So it's the maximum over all values of the index. So it's the maximum absolute value of any of the elements. Okay. All right. Now, as an example, suppose x is this vector, 1, 2, and minus 3. We go ahead and compute the norms. So the 1 norm that would be 1 plus 2 plus absolute value, so we get 6. The 2 norm would be square root of 1 plus 4 plus 9, so the square root of 14, which is going to be between 3 and 4. And then the infinity norm, well, that's going to be the maximum of the absolute value of all the entries. So it's going to be 3. Notice that as p increases, the value of the norm decreases, because what's happening is it's like all of the elements are given equal weight in the 1 norm. But as you increase p, the smaller elements, or anything with the largest, you give less and less of a contribution. And so by the time we get to the infinity norm, we're not making any contribution at all. Okay. Alrighty. Oh, it's exactly 6:15. So that's where I'll stop. So pick up with vector norms on Wednesday. Okay. Oh, I'm so sorry. I forgot to turn this. Wait. No? Never mind. I'd written that earlier. So, okay. I will post the video tonight, and then now that the software licensing snafu is settled, we should have full lectures from Wednesday on. Okay.
Okay. I haven't eaten it yet.
So I'll hear you on Wednesday, Janae?
Yeah, I just mute it so that you don't hear any background music from me.
Oh, yeah, that's
Yeah,
fine.
but I'll be online.
Okay. All right. See you then.